Okay, so thank you very much for coming. This work was done in collaboration with a bunch of other people at both Julia Hub and the University of Washington. Fortunately, I couldn't list them all here, but thank you very much if you know who you are. Their help is essential in getting Julia to fly, quite literally. So to illustrate where I'm going with this, I wanted to play a quick little video. This is Julia running on the quadcopter. It's being used in closed loop here to run a 3-degree of freedom controller. The microcontroller that's actually flying the vehicle here is communicating a state estimate to Julia, which is then responding in real time to produce an acceleration demand that's causing it to fly in this circle. I'll be talking about two different implementation strategies that we took to get this working. One is what you're seeing here, and I'll talk about it in a second. And I'll also talk about some of the challenges that we faced along getting Julia into an embedded real-time environment. Okay. So I think that at this point we're all quite familiar here with Julia's arguments about solving the two-language problem. The idea is that Julia can give you like high productivity and high performance in the same language, et cetera, et cetera, et cetera, the old story. Normally when we talk about that though, we're talking about solving it in like a desktop-like or an HPC-like environment, maybe a little bit of GPUs on the side. At the same time, you see these same sorts of problems embedded in real-time control applications. You see a lot of people who are working in very high-level languages who then have to sort of fight to then get their algorithms or the implementations down onto the actual controller or the actual embedded platform that's ultimately controlling the system. And what we were interested in doing is asking can we use Julia to solve this kind of two-language problem? Can we use Julia to solve the two-language problem that we're getting in the embedded space? And today I'll talk about some proofs of concept for that. But as I say, like embedded real-time controller, there's sort of two descriptors there. There's two adjectives there that are worth discussing in a little bit more detail. So the first one is embeddedness. There's a lot of embedded computers out there, and there's sort of no single concept of what an embedded computer is other than it is a computer that is shoved into something else. They come in a wide array of form factors. So like on one end of the spectrum, you have what are basically, which orientation is this? On one end of the spectrum, you have what are basically just normal computers that are shoved into a ruggedized box. They have some funky connectors on them, but they're ultimately desktop class or server class hardware, tens of gigabytes of RAM, the normal OSs and CPUs you're used to dealing with. Julia can actually be used on these quite readily. It's basically a normal computer in a funky box. You then have more embedded platforms, stuff like Raspberry Pis. They have much smaller processors. You're talking about things on the order of gigahertz. They have lower IPCs at that. They have less RAM. They have less memory, but they're still desktop-y systems. These are commonly referred to in the embedded world as application class processors. They have MMUs. They can run Linux in simultaneous multiprocessing environments. They're still desktop-like systems. You can think of them like a normal computer, but they are easier to embed into larger systems. Then on the other side of the spectrum, you have microcontroller-like things. These are processors that are much simpler to implement into your system, and they also achieve much better real-time guarantees. But for that simplicity, you're paying a lot in terms of performance. So the sort of higher end of microcontrollers these days are talking 500 megahertz to 1 gigahertz. You're taking an even bigger IPC oof when you go down to these. And we go from talking about gigabytes of RAM to talking about megabytes of RAM and storage. And then on the very far end of these, we have like this image here is of the new like packaged world's smallest microcontroller from Texas Instruments. These things are still running like tens of megahertz. Kilobytes of RAM and are obviously extremely easy to implement, but for that you're paying a lot in terms of the amount of performance. And sort of what I'm interested in talking about today is how can we get Julia onto this whole wide spectrum of devices. Another qualifier that I mentioned was real time. There's sort of two aspects to this. I'll talk about both of them. And it's also extremely fuzzy. So the one way you can classify these real-time systems is based on what goes wrong if you don't meet whatever definition of real-time you have. So like on one end of the spectrum, you have stuff like video games. It's important that a video game gets back to you quickly, or else you have the frame will stutter. But it's ultimately annoying. Like it's kind of okay if you drop from 60 FPS to 51 FPS in a video game. No one cares that much. On the other hand, on the other side of things, you then have hard real-time systems where if it goes wrong, if it misses that deadline, then everything goes to hell. So in this example that I'll be talking about today of the quadcopter, if our translational controller suddenly takes you 1 second to get back instead of 10 milliseconds, the quadcopter will go into a wall. And that's not a desired outcome, and it's relatively low stakes here. Hard real-time systems can get a lot trickier than this. For example, in electrical control, if you miss a microsecond deadline, you might be talking about getting 24 volts through on a 3.3 volt bus, and nobody likes that experience. That said, this taxonomy, like you'll hear these terms a lot. This taxonomy is really fuzzy, depending on who you're talking to and what domain they're working in and what context it is. All of these will be different. Another aspect to this real-timiness is the time scale that you're working at. You can go from nanosecond latency, you'll see these sorts of requirements in like RF-direct digital synthesis or optical systems, all the way up through to hectosecond time delays. And all of these are still real time, they're just different definitions of what it means to be real time, driven by when you need to get the answer back. Let's see, right. Okay, so to quantify this a little bit for this specific talk, I'll be talking about flying the University of Washington Autonomous Control Laboratory quadcopter using Julia. There's two different major processing devices that are available on this platform. One is a Raspberry Pi CM4. It has a quad-core application class processor like I mentioned earlier. It's running Raspberry, and I'll talk about this in more detail later. So this is sort of acting as a sort of higher level computing platform. The lower level computing platform, the thing that actually does the hard real-time control on the quadcopter for the most part, is the STM32H745 microcontroller, which has a Cortex M7 running at 480 megahertz. This is, as I mentioned, a hard real-time application because if the controller doesn't get back to you in a lot of time, the quadcopter goes into a wall, and the quadcopter does not enjoy this experience. Ask me how I know. For this application, our control loop is running at 100 hertz, so we'll have about 10 milliseconds. 10 microseconds is very different in order for a controller to be able to meet its deadlines. In terms of broad software architecture, the low-level drone control is being done, and as well as state estimation is going to be done by the standard PX4 autopilot. The way that all of these systems that I'll be presenting today work is by having PX4 produce a state estimate that's then sent across to Julia through some mechanism. The vagueness is intentional here. And then Julia will compute a desired control output and send it back to PX4 to be executed by the quadcopter. The flight plan for all I'll show you today is to fly in a circle. This is a very sophisticated, complicated trajectory described by 3 lines of code. We're doing position, velocity, acceleration control in 3 degrees of freedom, and then the attitude control of the quadcopter is then handled by the built-in PID controllers running on the microcontroller in PX4. So we're just producing a thrust demand here. We're not doing attitude control at this point. The control law is a very straightforward geometric controller. It's actually literally implemented in 1 line of code. The throttle is calculated as the desired throttle is calculated as a function of the position error, the velocity error versus the feed forward. We also produce have a gravity feed forward term, and then it tries to track the desired acceleration. We then finally have a projection onto the orientation of the quadcopter because of the differential flatness to make sure that we don't go flying off in totally the wrong direction. So the first architecture that I'll be talking about today is actually not an embedded one at all. This is software in the loop. So here, what's happening is that I have the controller that's running in Julia on a normal REPL on my normal desktop with all the normal web browser-y stuff that's going on in the background on the same desktop. It's then communicating over UDP via loopback and the Xeno messaging middleware through a router and then to the PX4 flight controller, but this time also running on my desktop. PX4 then has its own CIDL support that then allows it to control a virtual drone rather than a physical drone. And then it's then sending those updates to the gazebo simulation that is then simulating the drone in 3D, and then that state is then being propagated all the way back through PX4 all the way to Julia. So there's quite a long round trip all in a not real-time environment happening here. And you'll see why I'm adding all of these qualifiers in a second. So for an example of what the trajectory ultimately looks like, and you'll note that the circle changes size through most of this. What we do is the drone will start at an initial position, and then it will sort of start tracking the circle. And here, because the gains are sort of tuned down a little bit to keep the drone from being too aggressive, we're getting close, but not perfectly tracking it. So the reason why I mentioned the not real timiness is as an example of the performance that we get in this setting. When we have the built-in controller running, so this is running in PX4, which is then removing a lot of the scheduling and the networking stack out of the equation, we're seeing that there's like 0.7 milliseconds of variance, which is reasonable in this setting. Again, we have a 10 millisecond budget here. Where it gets a lot more exciting is when we switch over to the Julia controller running in the REPL, when the outliers are starting to get concerningly close to that 10 millisecond budget, and our variance overall is about 2 milliseconds of delay. A lot of this is then likely coming from running on a normal desktop with all of the normal background applications. But at the same time, that desktop is a lot more powerful than the Raspberry Pi, for example, that we'd be implementing on. So early on, there are some interesting challenges, let's say. So let's talk about that first implementation onto the Raspberry Pi. The architecture that we're using on board is ultimately extremely similar to the one that we're using in the CITL simulation, quite intentionally. Except here, instead of having both PX4, the underlying flight controller, and the Julia flight controller running on the same physical hardware, we're splitting them. Now the Julia flight controller is running on the CM4, the Raspberry Pi, connected via Ethernet to the microcontroller that's then running the low-level flight controller. The low-level flight controller is then sending state estimates back over Ethernet to Julia. Julia is then doing its computation and then sending the command acceleration back to PX4 to actually execute. The way that we're calculating timing in this setting is that we're running a hardware timer on the microcontroller. So the microcontroller, when it sends a state estimate back to the CM4, is starting a hardware timer running at the clock speed of the microcontroller, and then when it gets that acceleration demand back, it then stops that and records that. So that's how we're measuring the timings. Getting this to work had some interesting challenges. So like I mentioned, we're running on a Raspberry Pi Compute Module 4. It's essentially Raspberry Pi 4 in a slightly more embedded application. We're running Raspbian without special real-time extensions. So it's normal Linux. We're not running RT Linux here. We wanted to avoid like running the JIT. We wanted to avoid running the GC, and we coded for this, but we wanted to keep the size down because our Raspberry Pi is not actually a very good one. We only have about 2 gigabytes of free memory on board the platform. And we wanted to do as much of the compilation off-board as possible. So the solution that we adopted to that was JuliaC, which ended up working quite well. I won't go into too many of the details for how we did this. If you're interested in more details on JuliaC, please see Jeff's talk later today on trim. Some of the specific challenges that we ran into that I want to talk about, though, is that Julia doesn't currently support cross-compilation. You need to run JuliaC on the same architecture that you're targeting. My computer that I did this work on is x86-64, and the Compute Module 4 is running AArch64 ARM. The solution that we came to was we compiled this using a GitHub Actions ARM runner. If you're interested, the GitHub CI setup is available online. I'll have this again at the end of the talk if you're interested. This sets up all the dependencies and compiles it with some caveats that I'll talk about at the end, though there are some works. So in particular, you have to set up the artifacts by hand, and it would be nice in the longer run to produce a Docker image that you could just sort of set up and run that has everything built in. So ultimately, what we were able to do is we were able to take the Julia code that we had and then compile it down to a 2.2 megabyte binary plus about 160 megabytes of runtime dependencies that were pulled in by Julia to make it all work. We likely could trim this smaller, but this was small enough to fit on the Raspberry Pi with room to spare, so we were happy with this. So I just also wanted to add some really important caveats here before I present the timing results. It's measured on the microcontroller, and it also includes networking latency, so the latency required to get from the microcontroller to the CM4, the non-real-time Linux execution on the CM4, and then the serialization and deserialization overhead that's happening both in Julia and in the microcontroller. Does this work? So yeah, so this is just the earlier This is just the earlier video that I showed you. So this is running with that. This drone here is being controlled through the architecture that I mentioned. The Raspberry Pi is physically on the drone, communicating to it over Ethernet, and then driving it around in a circle. And let's see, I think. Right, so then the timing for this one, despite the fact that the Raspberry Pi is noticeably less powerful than my desktop by a considerable margin, the timing for this was considerably better. We were able to achieve a median response time of about 6 milliseconds, which is somewhat of an improvement, but we have a more comfortable margin between the timing outliers and our 10 millisecond timing budget. Additionally, we reduced our overall response time variance by about a factor of 2. So we went from about 2.2 milliseconds to 1 millisecond of response time. One note that I would make here with this particular graph is that the initial controller, the built-in controller, is being based on a different position estimate that's coming out. This will cause the built-in controller, the one that's stock with PX4, to always show up at about the 10 millisecond line because it's running one control loop out of phase. So the reference here should be made to that 10 millisecond line rather than 0 milliseconds. The next architecture that we looked at, that we got Julia running in, is actually running Julia on the microcontroller itself. So this is running Julia on the Cortex M7. Here we eliminate all of the networking. So it's actually being built into the same executable that PX4 is. It's just running as part of the PX4 system, as part of the NetX real-time operating system. And the compilation approach that we adopted here is very much inspired by MCU compiler, based on static compiler, and is built on top of the GPU compiler infrastructure. Getting Julia to run on the microcontroller was a bigger adventure than Trim. Getting Julia to run with Trim was pretty easy. We had to work on some small features, but it ultimately fairly straightforward. Getting it to run on the microcontroller took more work. We needed a specially compiled version of Julia. Julia doesn't normally come with the ARM v7 target that you need to get it to run on the Cortex M7. And the floating point support in LLVM on Cortex M7 or ARM v7 has some interesting warts. In particular, despite me thinking that it says hard float in it, the thumb M7 none EABI HF does not actually make it generate hard floating point instructions. So that was a bit of fun. And we ended up having to use LLC directly because because LLVM doesn't expose this very well through the API. Let's see. The ultimate architecture that we ended up with for compiling to the microcontroller target takes Julia, sends it through static compiler. We end up with LLVM IR in a textual format, which we then compile with LLC into a 1.5 kilobyte executable. So this is really, really small and fits into the 2 megabyte overall program memory quite nicely. We then statically link that using normal GCC LD in with the rest of the PX4 flight controller code, as well as the shim that intermediates between Julia and the rest of PX4. And then we end up with the native executable. It's not perfectly 2 megabytes. I think it's like 1.995 megabytes. But again, I'm quite happy with that. We have 2 megabytes of memory. Let me play this. Yeah. So this is the drone flying Julia on the microcontroller. So it again starts, the circles, has changed size and position a little bit. But here it's able to successfully track the trajectory. It works, ultimately. Right, so timing on this. Now that we've managed to eliminate most of the overheads, the performance, the end-to-end performance on this is a lot nicer. Despite the fact that the microcontroller is a lot slower, to put it mildly, than the CM4, because we're able to avoid the networking overhead, the non-real-time OS, all of the things I mentioned earlier, it becomes so fast it's actually quite hard to measure on the microcontroller. The mean of this was about 7,000 clock cycles, and the minimum, so probably the actual execution time if we didn't have RTOS interrupts happening, et cetera, in the interim was about 4,000 clock cycles. And obviously the variance also drops dramatically because there's frankly a lot less time for exciting events to happen. So in conclusion, you can use Julia in real-time on embedded systems. There's a couple of ways you can do it. We're able to achieve both millisecond level latency through a network-based approach using Julia on a companion computer connected to a microcontroller, as well as microsecond level latency by running Julia directly on the microcontroller. You can deploy Julia onto application class hardware in a very straightforward way, in spite of relatively constrained memory for application class hardware. If you're interested in more details on that, check out Jeff's talk. I'll have links to my work on the next slide. The results were way faster and smaller than package compiler. Like JuliaC was able to compile our code here in seconds versus when I tried to do this with package compiler, which I don't think actually finished. Another thing that I want to mention, and if you're interested in this, is that Julia has a lot of opportunity to work very well with ROS. As part of implementing this, we implemented a native Xeno binding, and we think that we can get Julia working extremely cleanly with ROS. If you're interested in more details on this, please talk to me afterwards. Following on from that, deployment onto microcontrollers directly is possible, but it's still pretty immature. So we had a number of issues along the way. In particular, floating point support on ARM v7 needs some work in order for this to be widely usable. Though experiences, if you're using a much more modern microcontroller that runs ARM v8m, might be better. So finally, just to wrap up, the code is available here. You can go to, if you just search these on GitHub, you should find these examples. I would suggest that if you're interested in this, you should probably actually look at the application class example, but the microcontroller example is still very proof of concept level rather than something that I would suggest that you think about production with. Okay, thank you very much. Any questions? Yes?
Yes, thank you.
Please wait for the...
Thank you. Regarding Julia on the microcontroller, did Julia have to communicate with the sensor hardware and the motor hardware through I2C, SPI, or others, or was it isolated from that?
So in this application, it's isolated by the driver stack provided by PX4. So we're actually a couple of levels abstracted from that. PX4 is doing the low-level I2C and SPI support. So in this particular application, all of our sensors are SPI-based. That's then filtered by the C++ extended Kalman filter built into PX4, which is then producing the state estimate that we're using. That's also doing fusion from the vision system you saw in the pictures. So we're not doing ultra low level stuff like that yet.
Even when Julia was on there?
Correct.
I have a question about the cross compilation.
Yep.
Are you aware of any even experimental things in the works that would allow you to do cross-compilation on Julia?
I'm not sure. I wouldn't be the person to ask. If you're interested in that, talk to maybe Cody or Jeff.
All right, thanks.
How hard was it to get GitHub Actions to get the right target that matched what you needed to build to do the compilation for your architecture?
Super easy, actually. Let me... let's see. Yeah, okay, so the two things that were needed was this line, which makes it use the GitHub Actions ARM runner, and this line, which makes Julia pick the right ARM target. That was all. So this was by far and away the easy part.
Do you have to write like special Julia code for this, or it's like generic way of doing regular Julia code? Right.
The trim code, like the JuliaC code, that I would say is just you are very careful about performance brain. Like you need to be careful about your allocations. I strongly recommend if you're in real time you not. And but ultimately you're aiming for sort of a very normal target of no dynamic dispatch, very carefully managed allocations, that sort of thing. So fast Julia code would be what would be for JuliaC. For the microcontroller, completely different ballgame. You need to like change your brain to think embedded in microcontroller rather than normal Julia. I think that's one of the big questions about like going forward with targeting MCUs is how can we exploit aspects of the Julia ecosystem to avoid having you to completely change the way you think in order to live within the constraints of the hardware.
So for the MCUs, you get rid of dynamic allocation completely?
Yes. Yeah. So it's the same pipeline that's used for GPU kernels, for example. So they're completely allocation free. Any other questions? All right, thank you very much.